This video is sponsored by Radiacode. In 1862, the French Academy of Sciences published a report that contained a groundbreaking idea. However, nobody paid attention to it, and it went largely unnoticed for many years. But the idea described in this paper would become one of the most important fundamental concepts in all of science. This is the story of how the newest science in the world, chemistry, went from being a disorganized mess where nobody could agree on anything to the scientific juggernaut that it is today. One of the craziest things about this story is that this revolutionary report wasn't even written by a chemist. It was written by a French geologist called Alexandre-Émile Begoyer de Chancourtois, who was 42 at the time. To understand his paper and its significance, we need to go back a couple of years. You see, although there had been a huge amount of progress over the previous century, including Antoine Lavoisier's establishment of the definition of an element, and John Dalton's introduction of atomic theory as just a couple of examples, by the mid-1800s, the world of chemistry really was quite chaotic. Most chemists had accepted Dalton's proposal that all of matter is made of atoms, but nobody could agree on how those atoms were arranged or how heavy they were, and this was a huge problem. You see, back in those days, chemists had no way of measuring the mass of a single atom, and they wouldn't be able to until the invention of modern mass spectrometry after the First World War. However, they did agree that hydrogen had the lightest atoms of any element, since hydrogen gas had the lowest density. So, hydrogen was assigned an atomic weight of 1, and all the other elements' relative atomic weights could be calculated from there. But this is where things got complicated. Different chemists had different methods for determining these relative atomic weights. Since John Dalton was the one who first introduced atomic theory, let's take a look at how he determined the atomic weight of oxygen. The first ever mention of atomic weights was in a paper published by Dalton in 1805, where he described his investigation in which he found that, for some reason, water absorbed different amounts of different gases. Towards the end of the paper, he said, "The greatest difficulty attending the mechanical hypothesis arises from different gases observing different laws. Why does water not admit its bulk of every kind of gas alike? This question I have duly considered, and though I am not yet able to satisfy myself completely, I am nearly persuaded that the circumstance depends upon the weight and number of the ultimate particles of the several gases, those whose particles are lightest and single being least absorbable, and the others more according as they increase in weight and complexity. An inquiry into the relative weights of the ultimate particles of bodies is a subject, as far as I know, entirely new. I have lately been prosecuting this inquiry with remarkable success. The principle cannot be entered upon in this paper, but I shall just subjoin the results as far as they appear to be ascertained by my experiments." Beneath, Dalton casually dropped the first ever table of relative atomic weights. But where did he get these numbers from? In Eric Sherry's book on the periodic table, he explained that Dalton used Lavoisier's data on the composition of water, namely 85% oxygen and 15% hydrogen. Assuming a formula of HO, Dalton calculated the weight of an oxygen atom to be 85 over 15, which equals approximately 5.5. But wait, why was Dalton using HO as the formula for water? Well, it was well known that water was a compound of hydrogen and oxygen because when you react the two gases together, you get water and nothing else. As a part of his original atomic theory, which he published in full in 1808, Dalton included what became known as the rule of greatest simplicity. With no way of knowing how atoms combine to make molecules, he stated that nature would never be more complicated than it needed to be. So he assumed that atoms always combine in the simplest possible ratios. So, in pure elements such as hydrogen and oxygen, the atoms floated around as individual atoms. When they combined to make binary compounds, as he called them, they would always do so in a 1-to-1 ratio. So, water being a binary compound of hydrogen and oxygen would, according to Dalton, form in the ratio 1 hydrogen to 1 oxygen, giving it a formula of HO. For this publication, Dalton made his own measurements of the amounts of hydrogen and oxygen in water and found that the ratio was closer to 7. With these new measurements, he included an updated table of relative atomic weights. All of this was really incredible work, but it didn't take long before other chemists began challenging Dalton's assumptions. Just a few months after Dalton's publication, a French chemist called Joseph-Louis Gay-Lussac took a closer look at the volumes of gases as they reacted. He found that 2 volumes of hydrogen always reacted with 1 volume of oxygen to form 2 volumes of water vapor. He observed that similar simple ratios were always present between reacting gases, and defined what he called the law of combining volumes, which stated that the ratio between the volumes of the reactant gases and the gaseous products could be expressed in simple whole numbers. Inspired by Gay-Lussac's work, in 1811, the Italian chemist Amedeo Avogadro hypothesized that since these same simple ratios could be found between all reacting gases, it follows that at the same temperature and pressure, equal volumes of any gases contain an equal number of molecules. This became known as Avogadro's law, and it would mean that Gay-Lussac's observation could also be interpreted as 2 molecules of hydrogen plus 1 molecule of oxygen gives 2 molecules of water. And therefore the formula for water must actually be H2O, not HO as Dalton had proposed. This in turn would mean that Dalton's calculation for the relative atomic mass of oxygen must also be wrong. It also suggested the existence of diatomic molecules. But Dalton didn't like any of this. He was stubborn and mistrustful of other chemists' work. The brilliant English chemist Humphrey Davy described Dalton as a very coarse experimenter who almost always found the results he required, trusting to his head rather than his hands. Dalton vehemently disagreed with Gay-Lussac and Avogadro's conclusions. Very little was known in these early days of atomic theory. If you watched my previous video, you'll know that it took almost a century before the Curies introduced the world to what Marie called radioactivity. But are you curious about how much radiation you're being exposed to right now? If you are, check out Radiacode. Radiacode makes next-generation smart devices which can be used as a radiation detector, dosimeter, and spectrometer. They're perfect for adventurers and explorers who are interested in science. I wanted to test it out by visiting one of London's most iconic landmarks, Wembley Stadium, to see if I could detect any radiation nearby. The Radiacode app has a really cool radiation mapping feature where it produces a color-coded path so you can see if there are any radiation hotspots on your route. The device itself also has an alarm feature that goes off when it detects a spike. When approaching the famous Wembley steps, the alarm told me that the radiation had increased to around 20 counts per second, or 0.15 microsieverts per hour. Even though this seemed dramatic, this actually still falls within normal background radiation levels, so there's nothing to worry about here. But it does show you how incredibly sensitive the device is. Check out my link in the description to start adventuring like a scientist. Okay, back to the video. So, from very early on, chemists were divided about relative atomic weights and chemical formulas. Most were Team Dalton. Very few were Team Avogadro. A big problem was that there wasn't any direct evidence for Avogadro's law, so it just didn't gain much traction. I mean, to be fair, there wasn't any direct evidence for Dalton's rule of greatest simplicity either, but maybe since he was the actual founder of atomic theory, Dalton's word counted for more than Avogadro's at the time. By the way, I have an entire video all about the development of atomic theory, from the ancient Greeks to Dalton and all the way up to the atomic bomb, so I'll link that below if you want to learn more. To complicate matters further, in 1813, just 5 years after Dalton published his atomic theory, the Swedish chemist Jöns Jacob Berzelius published his own method for determining atomic weights, where he assigned oxygen an atomic weight of 100 and compared all other elements to this. He thought that this was a better method because oxygen reacts with most other elements, so it's useful for finding the ratios between the masses. However, these alternate relative weights just complicated matters even further. Over the years, the confusion only grew. Different reference standards, different methods of experimentation, and different methods of calculation. Depending on whose publication you were reading, you might see different atomic weights being referred to, which led to different chemical formulas. On top of this, chemical notations and chemical nomenclature all varied massively. Here are 19 different formulas for acetic acid which were all simultaneously being used in the mid-1800s. They can't all be right. Which one was correct? Obviously, this was a huge problem, and the more time went on, the worse it got. In 1860, a 31-year-old German chemist called August Kekulé had finally had enough of the mayhem and decided that it had to be sorted out once and for all. So, he enlisted a couple of his colleagues to help him arrange something the world had never seen before. He wanted to invite all of the top chemists on the planet to come to one location to hash out all the major problems in chemistry, including chemical nomenclature, notation, and atomic weights. This was to be the world's first ever international scientific congress. By the way, this Kekulé character had just a couple of years earlier proposed his theory of atomic valence, which stated that different atoms always make specific numbers of bonds to other atoms. For example, hydrogen makes 1, oxygen makes 2, nitrogen makes 3, and carbon makes 4. Using this principle, he was able to introduce the best theory of chemical structure to date, particularly in relation to carbon-based molecules, and as such, he was one of the founders of organic chemistry. It also suggested that water would indeed have a formula of H2O, not HO. My very first video on the history of chemistry talks a lot about Kekulé and his work on benzene, so I'll put a link in the description if you want to check it out. 140 of the world's most prominent chemists attended the conference, which took place in Karlsruhe, Germany. On the first day, on the 3rd of September 1860, the General Secretary of the meeting, Karl Velzin, addressed the audience and said, "For the first time, the representatives of a single scientific discipline have met, and it is the youngest science. We represent different countries and speak different languages, but we are related by our craft. We are gathered for the specific purpose of attempting, in good conscience, to prepare the way for unity on points of significance for our beautiful science." Over the next 3 days, there was a lot of fierce debating between the attendees. One thing they did agree on was that the chemical notation system devised by Berzelius should be adopted. Berzelius had proposed a simple system whereby 1 to 2 letters was used to represent each element, and subscript numbers were used to indicate how many of each type of atom were present. This was a lot more practical than Dalton's original system of notation, which used different circular symbols for each element. Since Dalton had passed away 16 years earlier, he wasn't around to fight for his system. By the time the third and final day of the Congress came around, the chemists hadn't agreed on much apart from Berzelius' notation. But it was on that day that a relatively unknown Italian chemist called Stanislao Canizzaro stood up to give his input. He gave a passionate, eloquent lecture arguing in favor of the work of his countryman, Amedeo Avogadro. He handed out reprints of a paper that he'd written a couple of years before, which hadn't received much attention at the time, but explained his arguments very clearly. One attendee, the German chemist Lothar Meyer, later wrote, "I was astonished at its clarity. The little manuscript covered all the important points in dispute. It was as if scales fell from my eyes, doubts vanished, and a feeling of calm certainty came over me." Although nothing was officially agreed upon during the Congress, over the next couple of years, Canizzaro's arguments were accepted amongst the scientific community. Avogadro's law was taken as fact. Finally, chemical formulas and atomic weights were all agreed upon. For the first time, chemists were all on the same page, and the field of chemistry joined its older siblings, biology and physics, to become a unified, systematic science. Now we can get back to our French geologist, de Chancourtois. As a geologist, he got a lot of satisfaction out of organizing and systematizing different minerals, and he wanted to see if he could do the same for the elements that made up those minerals. It was shortly after the Karlsruhe Conference that he started working on this, and he looked into the newly established atomic weights to see if he could spot any patterns. As I said at the beginning of the video, what he found would become one of the most important fundamental concepts in all of science. De Chancourtois noticed that when you order all of the elements in terms of atomic weight, something interesting happens. He illustrated this with a table that was 16 relative weight units wide, and diagonal lines that repeat down the table. So here's how it works. Hydrogen has a relative atomic weight of 1, so de Chancourtois placed a dot here, 1 weight unit into the table. Next we have lithium, which has a relative weight of 7, so its dot is here, 7 units in. Continuing all the way to oxygen, which has a relative weight of 16, we can see that it's right on the boundary of the 16-unit wide table, so it has a dot at the end of the first diagonal line and at the beginning of the second diagonal line. Following this is fluorine, with a relative weight of 19, so that's all 16 units from the first line plus an additional 3 units on the second line. He included every known element in his table and spotted something interesting. For some reason, there were several cases where elements that were very similar to each other seemed to coincidentally line up in perfect vertical columns on his table. For example, lithium, sodium, and potassium all line up one on top of the other. These elements are all reactive metals with similar properties who do the same exact reactions as each other, with the metals getting more reactive as you go down the column. It was long known that these metals were related, so much so that they already had a collective name, the alkali metals. There were many similar examples where the properties of elements periodically repeated as you went down the table. We could even call it a periodic table. That was exactly what de Chancourtois had done. He had created the first ever periodic table. De Chancourtois gave his table a name, Vis Tellurique, meaning telluric screw, since tellurium is located in the center. But why screw, you ask? Well, one thing I haven't mentioned yet is that de Chancourtois designed his table to be twisted into a 3-dimensional helix. Here it is in its full glory. When researching for this video, I found that the Science Museum in London had a century-old replica of the original telluric screw. After contacting them, they allowed me permission to visit their enormous storage facility to take a look at it. I saw some amazing stuff while I was there, and I'm planning on making a full video about the visit, so stay tuned for that in the near future. But the main purpose of my visit was to see the 100-year-old telluric screw, and it was beautiful. Seeing it in person really took my breath away. It really leaves you wondering why this didn't catch on when de Chancourtois first wrote about it. Well, as it turned out, there was a problem with the original publication. The journal didn't include the diagram in the article, just a description. As Eric Sherry said in his book, frustrated that the journal Compte Rendu failed to include a diagram, de Chancourtois had his system republished in 1863. But because it was published privately, this further article received even less notice from other scientists than did the original one. De Chancourtois' contribution was only fully appreciated many years later, but by that point, others had proposed their own periodic tables, including a few attendees of the Karlsruhe Congress, such as Lothar Meyer, and a little-known chemist from Russia. Maybe you've heard of him, Dmitry Mendeleev. Check out my video on the history of the periodic table if you want to find out what happened next. Before you go, I'd really like to ask for your help. Every one of my videos is a huge, time-consuming project that I make by myself in my free time, but I'd love to be able to divert more time and energy to them. If you'd consider liking, subscribing, commenting, sharing, etc., that would tell the YouTube algorithm that this video is worth watching, and it would really help me out. My goal is to get to 100,000 Chemistorians by the end of 2025, so if you made it this far and you want to help out the channel, I'd really appreciate your support. Also, if you're looking for more Chemistorian content, you can become a patron to unlock perks such as bonus videos, ad-free videos, early access, behind-the-scenes updates, Q&As, and more. Thanks for watching, and I'll see you in the next one.